So I thought you were going to put this as 39.
Yeah, maybe you're right. I was thinking that we had one in the bag, but we don't yet because the one we were going to put in the bag didn't go in the bag.
Yeah.
Still sitting outside of the bag.
Yeah, and well, you do have one in the bag. It's Moon.
Yes, it's in the bag, but it's not bag worthy. It's
dated
back burner.
bag.
You don't want to put the bag on the back burner. That's just burn the bag.
I'm not, what are we talking about anymore?
Haven't got the focus. Right, let's start this. So this will be
39.
Hope episode 39. Syzygy, episode 39, ridiculously large telescopes. And welcome back to another edition of the Syzygy podcast. I'm not astronomer Chris, and sitting opposite me is astronomer Emily. Hi, Emily.
Hello, hello.
So this week we're going to be talking about some news from a mountaintop in Chile. Big stuff happening over there, up on the mountains, way up off the plains, where it's desert, but on a mountaintop, which is always weird. Chile's a strange place. But there's interesting things happening over there. People have been digging over the earth to build something very big and something very special. Emily, what are we talking about? What's happening in Chile?
Well, it's only the biggest telescope in the entire world that's going to be built there.
Oh, my God. So, hang on. There's already some pretty stonking telescopes in the mountains of Chile, but this is an even bigger one because the other ones weren't big enough.
They're definitely not big enough. So I must put an asterisk, biggest optical and infrared telescope.
Right. Okay.
Of course, radio dishes come in hundreds of meters in size.
Well, I mean, radio. They're not even trying. But this is optical.
This is optical.
Okay, so wind this one back. What are we talking about? What's the news? Work our way into this one.
So we got GMT, which
GMT, Greenwich Mean Time. I know that one.
No, not GMT.
Because Greenwich, there's an observatory, and so they're moving the Greenwich Observatory to Chile.
No. We need to roll this all the way back.
Damn it, I thought I was on this one. Okay.
No, GMT, Giant Magellan Telescope.
Ah, okay. So the first thing that comes into my mind is there already a Magellan telescope?
Yes.
Right. Okay. So that was the average size. That's sort of the regular, just waking up in the morning and having a small Magellan telescope. But then you get to work and you really, really feel like you need a bigger one. So you go and get your giant Magellan telescope.
Yeah.
Yeah. Is the Magellan telescope currently, is that in Chile?
No.
No.
I can't recall off the top of my head where it is, actually.
You had one job.
I know.
To give us the background on the Magellan.
Well, I got too excited about the giant Magellan telescope.
Let's not get caught in the Magellan weeds here. We are building a bigger one than the one that currently exists. Do you know the one that currently exists, the Magellan telescope? Is that what it's called? Or is it like the sort of generic Magellan telescope? Is it?
Well, I don't really know.
Hang on. Look, I'm going to look this up.
Just edit this all out.
No. I'm not going to edit it out. I'm going to go and look it up. Yeah, no. Magellan telescope. Here we go.
Jeez.
Look, okay. Wikipedia, Magellan telescopes, pair of 6.5 meter diameter optical telescopes located at Las Campañas Observatory in Chile.
Oh, okay. So it is at the same place then.
Yeah. So there you are.
So we tried not to tell you my lies.
Yeah. But they're only 6.5 meters. So they're not giant. They're just your average 6.5 meter telescopes. So they're already pretty good.
They're all there.
So giant. How giant is giant if 6.5 meter isn't giant? I mean, 6.5 meter, that's the diameter of the mirror.
That's right.
Yeah?
Yeah.
That's really big.
Yeah, so if you've got a telescope at home, it might be a few inches in diameter.
You're lucky. Yeah,
right?
yeah.
Our biggest telescope on the Astro campus is 16 inches, the
16
mirror.
Inches, not feet, not meters, inches.
The research telescope I use pretty regularly is a meter.
Yep.
In diameter, and that's fairly small on the international scale.
But I mean, that's professional grade, proper research. Let's look at the skies properly, not as a joke.
Exactly. Yeah.
And that's 1 meter.
That's 1 meter.
And so these Magellans, just the ordinary common or garden variety Magellan telescope, is 6.5 meters. Like that's bigger than the width of your office. And you've got a very large, luxurious office here at the University of York, Emily. But it's bigger than your office. That's big.
That's big.
So question remains, how big is a giant Magellan telescope?
It's going to be 24.5 meters.
Shut the front door. That's really, really big.
It's very, very, very big.
That's a single mirror?
That is not a single mirror. It's going to be composed of 7 primary mirrors.
Right, but all with a combined area. Because once you get up to that size, I'm guessing it's pretty hard to get one big stonkin' 20, what is it? What did you say?
24.5.
24.5 meter mirror. That's stupidly big. You're starting to talk playing field size. So you can't do that in one go terribly easily. So you break it up.
And there's kind of two main ways that we do this. We do it, so the current world's largest telescope is the South African Large Telescope, or SALT, and that's just over 11 meters in diameter. So we're talking about more than twice that size already.
And is that one a single mirror, or is it broken
It's
up?
not a single mirror.
Right.
It is made up of hexagonal segments, which are about a meter in size.
Right.
So that's one way to do these giant mirrors, is to do sort of hexagonal things that are about a meter. This is a kind of a new way that they're doing with the GMT. Instead of having hundreds of smaller mirrors, we're having 7 incredibly large mirrors. Each of these mirrors is about 8.4 meters across.
Wow. So each of these alone is bigger than the generic Magellan telescope. And we've got 7?
7 of
Of them?
Yeah.
That's nuts. That's off the charts.
So these are the biggest single mirrors that we are capable of manufacturing in the world.
And one of them's not enough. Let's throw 7 of them together and make a stonkingly huge. That's what it should have been, the stonkingly huge Magellan telescope. I'm going to write to them and suggest a name change. Because, I mean, this is the point, isn't it? It's not built yet.
It's not,
Right.
no.
What's in the news then?
So actually, this is kind of an update on progress, which is really, really exciting. We've been waiting for GMT for a very, very long time. And I hate to say we're going to be waiting for quite a long time more. But we have just finished the excavations a couple of months ago of all the groundworks that are on site. So that means they had to dig out some of the rocks and so on. This is at Las Campanas Observatory, LCO. In Chile, and it's an existing observatory. There's a lot of telescopes already on site, so they chose kind of a knoll that's near to that part of the observatory.
I mean, there's a bit of space up there on top of the mountains. in
Quite a
Chile.
lot of space.
It's quite an empty spot.
But you've got to do some sort of foundation work, excavations. They've dug a big pole to put in some of the stuff which will eventually build up to become the stabilizers and things like that for the telescope. So that whole part, the digging up the ground part, is finished.
Right. So the news part of this story is, hey, fantastic, we've stopped digging and we're now building stuff.
Yes.
Which is cool, but it does sort of give us a little catalyst to be able to talk about this amazing, incredible telescope. It's going to be able to do extraordinary things. Just in the little bit of reading that I did in my extensive preparation for this recording.
Which didn't involve looking up the original Magellans either.
Well, no, but, who are you to talk? Thanks, Emily. Who's the astronomer? Put up your hand if you're actually an astronomer. Thank you. So that's the news part, which is that it's actually being built now. When is it due to actually be switched on and used?
Well, first
Do you switch
light-
on a telescope? I guess you must these days.
Oh, yeah, you definitely do. They have it's called first light. It's a really important part for any telescope. The first light that hits the mirror, from the universe. I mean, it's kind of a nice.
But I'm just trying to figure out, how does that work?
Way of
Is it
thinking about
do they have a big sheet covering over it and they pull the sheet off and it's first light, or do they have a big sort of roof over the top and they open that and that's first light, or like what? Is someone standing in front of it and then steps out of the way? How do you turn on the telescope?
It's going to be really interesting. It would be cool to see what they do. But one of those things or something similar, I imagine.
I'd like to see the big sheet. I'd like to be the big sheet, and then it's just ta-da, and someone just whips the sheet away, and there it is. I think that'd be great.
Yeah,
especially if someone had then sort of scrawled in lipstick or something. Done a big picture on the mirrors. I think that would be kind of cool.
They're probably just going to turn it on and go, oh, why isn't that not working? Oh, why is that bit not working? Oh,
yeah.
Can someone get out and fix that bit, please?
Yeah,
oh.
they'll turn it on for all the world's press and everything, and then they'll go away and go, oh, it's not working. Don't tell anyone. It's quick, fix that.
Plug that bit in.
Yeah, yep. So, okay. We need to wind this one back. There's so many questions. Giant Magellan telescope.
Well, hang on. You started asking me a question.
Did I?
Yeah.
What was it?
When is first light?
Oh, yeah. Did we not get to that?
I thought we got too excited about the sheep.
Oh, okay. All right. So when are they going to whip the sheep
Well,
off?
first light is going to be 2026 approximately. Now, it's not going to be the entire telescope that's going to be operational at that point.
Oh, right.
There's only going to be 4, maybe 5 mirrors on the telescope at that time. So there's going to be another 3 or 4 coming. There's going to be 8 mirrors in total where they can sort of swap out one when they need to do technical work on it. So polishing it and setting
So they'll have a
up
spare.
again. Yeah, basically.
Yeah. But that kind of implies that this is this is non-trivial, right? You kind of think, well, yeah, big mirrors, but I mean, how hard can they be? That's like 6 years away or more, 7 years away. You can't make 8 mirrors in 7 years and get them over to mountaintop and install them in Chile? You can only do 4?
No.
This is a very
we're
difficult...
hoping maybe 4.
Wow. So that'll probably be 3 then.
This is a process which is well underway. It's not like we just haven't gotten around to making these mirrors yet.
Yeah.
The first mirror was cast all the way back in 2005.
Seriously? Holy cow. That's crazy.
Yeah.
That's like almost 15 years ago. That's nuts.
So the point is that making these mirrors is hard.
Apparently.
It takes a really, really long time.
Apparently. Wow. So is this program like behind schedule, or was it always going to be, you know what, let's start building the mirrors now and in 20 years we'll have a telescope? Was that always the plan, or was it harder than we thought?
So, well, first of all, they had to make the first mirror in 2005 and get it up to a standard that was acceptable for the telescope before they would even commission the rest of the mirrors.
Wow.
So basically the mirror makers, who are a really fantastic group at the University of Arizona, the Stewart Observatory has a mirror lab. And that lab had to kind of build the first mirror as a proof of concept that we can do it, that it's going to be accurate enough to do the stuff that we want to do with GMT. And following on from that, then the following mirrors were able to be commissioned.
I just love the fact that they're doing, you know, tests on a mirror. Proof of principle on a mirror which by itself is the biggest mirror that we've got for a telescope. Like that's like let's just get that one working. You know, let's use that to have a look at the universe first.
Yeah. So there's quite a few 8-meter class telescopes around the world that have these single mirrors, and many of them were made at the Stewart Observatory as well. So it was just kind of, could they get it to the next level, if you like, of precision, which is required if you're going to put in several mirrors together.
Wow. Okay, so there's a lot of work to be done. Hoping for sort of half of them to be done by 2026, and that would be sufficient to be able to then have the switching on, pulling away of the sheet kind of ceremony to have first light and say this is an operational telescope, even though there's a few more still to come.
Yeah.
Yeah.
So maybe 2028 for the full mirror set to be there.
Fingers crossed. Okay. So this thing is made of, what did we say, 7 stonkingly huge mirrors. I mean, this is the only word that I can put on it.
Huge.
Really big to make one enormous mirror. The technology of those mirrors alone has to be off the charts. I mean, this is cutting edge stuff. So tell me about the mirrors.
Yeah, I'm a super fan, by the way, of the Mirror Lab that makes these mirrors. They do incredible stuff. So, and I talk about mirrors quite a lot when I'm teaching, because I teach students astronomy, so I talk about mirrors and telescopes. I also teach first-year students about optics, which is the optics of mirrors and how they work. And both of those, I can talk about these cutting-edge mirrors. So I really am a huge follower of these mirrors being made. We have 5 that have been cast. One of them is finished.
So the others are in a state of what? Construction and polishing?
Yeah. So the thing is with these mirrors is that they have to be ultra precise. So these mirrors have to be precise to 20 nanometers.
20 nanometers. So when you say precise, you mean the shape is well defined. You need to have it, curved, presumably.
Curved, yep. And
it's got to be to that, pre-ordered shape to within 20 nanometers, which is not a lot. It's a really small amount.
It's 1/1,000,000th of a centimeter.
Wow.
Or to give you an idea of how hard this is, these mirrors are spun out of glass. Mm-hmm. It's 1 glass molecule.
Good God. Now, when you say spun out of glass, what do you mean?
So this is super exciting. They take 20 tons of glass and they spend about a week heating it up, melting it, and then they start to spin it. So this is spin casting of mirrors, and this is why the Mirror Lab does such fantastic work from this technique. They spin it 6 or 7 times per minute when it's super hot. So this is more than 1,000 degrees, the glass at this point, molten. And then they slowly cool it over the course of about 3 months. And as they cool it, they very, very slowly decrease the rate at which it's spinning, so that the mirror slowly sort of comes into a general shape, but it also spins out lots of air bubbles and things like that out of the glass.
That's amazing. I love the fact that in this modern age of, we're so used to tiny computers with incredibly fine microchip technology and stuff like that, that we're still using glass and polishing mirrors down to incredible shininess. There's something, I know that the technology behind that is extraordinary. I'm not putting it down in any way, shape or form. There's just something, I don't know, kind of sort of old school and romantic about that. And I know
Yeah,
it's not.
yeah.
I know it's not some dude sitting there with a polishing cloth. I know it's not that. But it's also not too far away from that. They've got to polish these things.
They do have to polish these
with actual
things.
polishers.
With polishers, with robot polishers,
Yeah.
of course. So the robots have diamond wheels that once the mirror's cooled and sort of taken down, then they can start to polish it. And this is the bit that takes time, right? Going from something that's just cooled into hardened glass.
So it's been spun, it's got all the bubbles out of it.
Yep. And
But
then
then you've got to shine it.
The polishing takes years. That's what happens. So
And I'm guessing in an amazingly clean room environment.
Oh,
like
yes.
no dust is allowed in here. No, like don't breathe. You can't. I mean, spacesuits. I mean,
I don't think it's quite so bad because you can sort of brush dust a little bit and that off the mirror. But what they're doing is they're taking finer and finer grinding equipment. So they start off with kind of quite coarse stuff like coarse sandpaper, and then you go finer and finer in sandpaper. It's kind of the same sort of stuff. And by the end, you've got lasers which are helping the robot to measure exactly the shape of this
well,
mirror.
it'll have to be. If you're getting down to one glass molecule's worth of accuracy, you've got to be using laser technology to be able to help you measure that.
Yeah, well, just the technology to measure the shape of the mirror is fascinating because it's not symmetrical in spherical symmetry. So what that means is it's not the curvature is not the same on one side as on the other side. Because if you look at a picture of how this telescope is going to be assembled, each mirror has a particular position, and it has to be a different shape on the bit that's furthest away from the center than it is from the bit that's closest to the center.
So it's not just one big segment of a sphere. It's a different shape, or parabolic.
It's
presumably?
parabolic, yeah.
Which means that the mirrors are not. These aren't just slicing off a bit of an orange here. This is a really difficult shape, and you've got to do that really carefully. Wow.
And you see these pictures of these final mirrors, and the thing I love most about them is too. I mean, these aren't shiny in a sense.
What do you mean?
They're just glass. All we're doing is making a giant glass blank. We don't put the shiny aluminium coating on it until it reaches the telescope.
Oh, right. So, okay. So they're not mirrors yet. They're
not.
windows.
Well, they're kind of like big blanks. I don't know how you describe it.
So these are being made in America?
Yeah, so this is the Mirror Lab is underneath a stadium in Arizona, which is
Of course it is.
and wonderful in its own way. They built the Mirror Lab under the stadium to get power and to get a really big stable space as well. In fact, I heard a brilliant story about why these mirrors are 8.4 meters, because when they built the Mirror Lab and they built it underneath Arizona Stadium, they of course the stadium itself, which is above, has foundations. It has these huge concrete walls that support the rest of the stadium above it. There's only something like 9 or 10 meters between these foundations.
So they're getting together, the engineering team, and going, how big should we make these mirrors? Well, we know how big they can't be. They've got to fit between these big posts. So up to that, we're fine. Just make it a little bit smaller than that and we're good. And so 8 point what?
8.4.
Yeah, okay. Give
So
yourself
this is
a
why
little
we
bit of
have
slack.
the
Yeah.
biggest mirrors in the world at 8.4.
you
Not
are.
because we couldn't make bigger ones, but because we've got a stadium in the way.
Hey, look, call me stupid, but I would have thought that a stadium isn't the most stable environment. Like you got people playing sport and shouting and cheering and stomping directly above you. Is that really where you want to be making the world's largest and best precision mirror?
Yeah,
Really?
so, the foundations are very stable. So remember, this is underneath. So this
Yeah.
is like sub-stadium.
So it's not
stuff.
just under the bleachers.
And they built this stadium, right, to last. It's an incredibly well-built thing. And also there's a huge supply of power, which is quite helpful.
Makes sense.
Right,
Makes
so
sense.
lots of utilities on site. So it was a good choice, and actually there were 2 labs originally placed here. There was one doing things to do with trees and rings and trees. It was all set. So this guy Stewart, the Stewart Observatory was named after, was quite into quite a lot of different pieces of science.
He was a Renaissance man.
Yeah, the ring lab isn't there anymore for the trees, but the mirror lab is.
But the
still
mirrors
there.
are.
Yeah.
So why are we doing this? Why do we need a giant Magellan telescope?
Well, you always need bigger telescopes.
Well,
Chris.
yes. I mean, bigger is better. More expensive. I mean, can't be cheap.
No, it's definitely not. So we're talking about more than $1 billion US. Exactly how much, of course, we'll see.
Yeah, but let's say it's in the order of that number of zeros.
Yeah, a lot of zeros.
So I'm kind of hoping then that what you're going to get out of this telescope is some pretty good observing. So give us a sense for how good this thing's going to be. You don't throw $1 billion at a telescope unless you think it's going to be really good.
Yeah, definitely. So there's two ways we're really pushing forward with telescope technology with the GMT. The first one is pure size, and that what size gives you is resolution. And this is resolution, resolving power is directly proportional to how big your aperture is.
Okay.
So if you double the aperture, then you effectively double your ability to resolve objects in the universe.
Now, when we're talking about resolving objects, we're talking about the smallest details on the object that we can distinguish. So, a simple example might be that if you don't have a terribly powerful telescope, you see a blob in the sky. And if you get a more powerful telescope, that actually resolves, oh, right, that's a binary system. There's actually two things there. There's two stars.
Yep.
We couldn't see that because we didn't have a big enough telescope. Now we do. And hey, look at that. We can resolve the fact that that's two separate things very close together. Or we can resolve features that we couldn't see before. So this thing, with its huge diameter of combined mirrorage, is that a word? We'll be able to resolve much finer details than anything we've had before.
Definitely. And we're looking at something at least 10 times the resolution of Hubble.
Is Hubble the best we've got at the moment in terms of optical?
Not quite, no. So there was quite an interesting sort of story going on here because we started sending telescopes into space with Hubble. We've got several other space telescopes that are observing anything from planets to infrared light to ultraviolet telescopes as well. But we started to be able to improve ground-based technology so far that we were able to mimic what was going on with the space-based telescopes. So this is the second part of why GMT is really pushing the boundaries.
Okay, so the first part was just sheer size. Can we make one this big? But there's more to it than that.
Yeah, basically, can we make telescopes that exist such that the atmosphere, we can basically say, isn't there?
Right. And that's the point, isn't it? Because we started sending telescopes into space to get away from the atmosphere, because the atmosphere is a pain, right?
It's a giant pain.
And exactly why. I mean, let's just focus on optical for a moment. What is it about the atmosphere? It's the whole stars twinkle thing.
It moves.
Isn't it?
The atmosphere moves, which is just really annoying. So yeah, we get twinkle, twinkle, little star, right?
Yeah.
This is because you have parcels of air which are moving around in the atmosphere. They're also at different temperatures and pressures. So when you put light through it, it sort of bends around, it wiggles and wobbles. And by the time it reaches your telescope, your star is dancing all over the place.
Yeah, which when you're looking at it just with your naked eye up into the night sky, you see that as a twinkle. When you go up into space, turns out, apparently, I haven't been, but I have it on good authority, that stars don't twinkle. They're just little dots in the sky, which is one thing. But you can see the effects of the atmosphere in other ways as well. Like when you're driving along a road on a really hot day, which doesn't happen so much in this country, but in Australia or perhaps New Zealand, where we are from, driving along a road and the heat above the road causes mirages and things like that. It looks like there's, water ahead of you on the road, and it's just the light from the sky coming down and bending off the warmer air above the road. That kind of effect going on in the atmosphere above your telescope means, as you say, you're trying to look at this thing in the sky, a star or a galaxy or whatever it is, and it's moving around all over the shop, not twinkling, but just shifting. That means you can't get a decent view of it.
Yeah, it's blurry, basically.
Right.
Yeah. So we've developed huge amounts of technology to start to cope with all this and to start with cope with all the other effects that we have on Earth that we don't necessarily have to worry about when we're in space. So we have two classes of optical technology that we use. The first is active optics.
Active optics, okay.
And the second is adaptive optics.
Right. So there's no confusion there. So let's start with the first one then. Active optics.
So active optics, the good way to remember what the difference between the two is one is fast and one is ultra fast corrections.
Right. It's a little bit like the Magellan Telescope by itself is merely big, whereas the giant Magellan Telescope is seriously stonkingly big. Okay, so fast and stupidly fast. So let's start with the fast one. That's active
optics.
Okay.
Yeah. So these are changes that we make on the order of once per second.
Right. And what changes in what?
So we're changing the big primary mirrors, so these big 8.4 meter mirrors. And what we're able to do is move those mirrors around to adapt for changes in temperature. As the night goes on, the temperature outside changes. And it also helps us to account for gravity changing as we point the telescope in different directions.
Gravity changes? Sorry,
Well,
what?
the force of gravity on each mirror changes as you point it around. Because imagine if you point your telescope towards the horizon, you
Right.
get the forces start to shift around on the mirrors depending on exactly what
So
direction
what you're saying
pointing.
is these mirrors are so big that if we move them around, they actually start to bend and shift just under their own mass.
Yeah, and sag a bit.
Yeah, okay. And
So-
you can adapt for that on the timescale of sort of every second.
Every second,
You can
yeah.
adapt to changes in the temperature, changes in the shape of the mirrors due to just their sheer bulk.
Yeah, so you basically each of those mirrors is cast, it's solid, and then you're able to move each of those 7 mirrors just very slightly to shift them around to make sure that they're all still coming to a perfect focus point.
Wow. And so that's being monitored. That's the thing that's being monitored constantly is, forget about what we're looking at for a moment. Is all the light that we're collecting, is it coming down to a really nice fine focus? If it's not, start shifting things.
Yep.
Which I'm guessing takes an enormous amount of computing power.
Yeah, you've got big, what they call wavefront sensors. So these are constantly monitoring the focus of the telescope and using basically a similar system that's brand new to the GMT that they're developing. That works a little bit like LIGO, actually. So remember LIGO, we had 2 laser beams, point them in different directions, bring them back together and look at the tiny, tiny differences between those 2 laser beams.
Right. Yeah, LIGO that's the Laser Interferometer Gravity Observatory. Is that right?
Yep.
Yeah. That's the one that detected the gravitational waves.
Yes,
Okay.
yes.
Yep.
Yeah, so in that experiment, you put 2 lasers down enormously long tracks and then put them back together and see what the difference is basically between those 2 laser
And
beams.
you've got to be accounting for ludicrously small vibrations and changes in temperature and all sorts of things because the effects you're looking for are stupidly small. So you've got to get rid of as much noise as humanly possible.
Yeah, so it's kind of a similar piece of physics, actually, that you're manipulating. You're using lasers or wavefronts of light to check, are those light coming from all the mirrors? Is it always the same? Do you need to shift one of the mirrors back or forth just to make sure that all of those waves of light come in at the same rate?
Wow. Okay. So you're working at that at the time scale of, roughly seconds or every second. And that's fast. Mm-hmm. So that's active optics. And then there's the stupidly fast adaptive
optics. Yeah. So this is working at about 1,000 times per second, means tiny corrections. Now, instead of trying to deform these enormous mirrors, which are 8 meters each, and then the whole system together, instead of that, we deform the secondary mirrors. So these are the mirrors that, so you take all your primary mirrors, they focus the light towards a secondary mirror, which then often, in the case of the GMT, will bounce that light back through a hole in the middle, and all your instruments and so on that collect the light are at the back.
And you see this on some small telescopes even, don't you? Like
Yes,
there are
yeah.
some telescopes which are just the light comes in and it comes down and it goes to the eyepiece or to the camera or whatever it might be. But you've got others where it's got a bit of a larger bore on it typically. Bigger mirror down the bottom, maybe several inches. The light comes up to a smaller secondary mirror, actually at the entranceway or close to the entranceway to the telescope, and then bounces back down to its final resting place at the end.
Yep. It's called a Cassegrain focus.
Okay.
Yep.
So you're not adjusting the main mirrors on this one, because I'm guessing that trying to do that 1,000 times a second would be really hard. So how big are these smaller mirrors?
So
Much more adjustable.
They're a lot smaller and they're much thinner.
Right.
So that you can actually deform them. So there's about 7,000 actuators which are going to sit behind these secondary mirrors and basically bend them and warp them. And the reason why they're doing this is to back correct the effects of the atmosphere.
Okay, so in principle, I can understand that, but question, how the hell do you know what the atmosphere is doing 1,000 times a second to be able to correct for that?
Well,
You got to have some input information to be able to correct for it. Where's it come from?
So in science, we like to have a control,
Yes.
right? So we want to have a control in our, that we're looking at that wouldn't have any intrinsic motion of its own, that's only being moved around by the atmosphere. And the best way to create a control star is with a laser.
Now, we all know that lasers make everything better, but what's this laser doing?
So these are laser guide stars. So basically we use an enormous 5-watt laser, and that creates...
That's a lot for a laser.
It's a big laser,
Yeah.
yeah. And you might have seen pictures of these. They do exist at other observatories.
Yeah. You've got this sort of observatory, dome or whatever it might be in the background, and then this laser, often green,
Yeah.
shooting up into the sky, which I always thought was just for effect. It just makes it look cool.
It looks like
We've
they're
got
trying to zap
observatories
out
and
all the
lasers.
aliens in the universe. Right?
But it's not that. That's a, what do you call it? A guide?
Laser guide star.
Laser guide star. So how does that work?
So basically, we use a laser to create a fake star, artificial star, in the very, very top of the upper atmosphere. And then we know that light is perfect when it came out of the laser. That's what a laser is.
Yep.
And so we can, any changes, any wobbles that particular guide star does, we back correct onto the secondary mirrors, and it kind of undoes the effects of the atmosphere.
So you're shining a laser, and you know what that laser is. You know what that should look like if you were looking at it directly with nothing in the way, because you're making the laser, right? You're making the guide star. And then it's bouncing off the upper levels of the atmosphere down into your telescope, and you're comparing what you see with the telescope to what you spat out of the laser in the first place, or what you would expect if there was nothing in the way. And then you're adjusting that on the fly 1,000 times a second to make those two match.
Yeah.
Holy cow.
It's crazy.
That's off the charts. That's nuts. And that works?
It works. And I mean, we have done this on lots of our big telescopes, and the results that we've been able to achieve are on the order of being in space.
That's amazing. Absolutely amazing. I mean, I've heard of this stuff, but wow. I mean, when you get the details of it, it makes you realize just how big that is. How long has that idea been around?
Oh, it's been around for at least a decade now.
So it's still pretty new.
Yeah, it's pretty new. And
I mean, that must have been amazing when it actually worked the first time. It was just like, I can't believe we're doing this.
So I've seen some fantastic before and after images from particularly Gemini telescopes. And when they installed their laser guide, they took some pictures of bullets of Orion, which are these kind of... they look like they're tiny little passes of gas that are moving incredibly quickly. And the resolution of the image doesn't really change because the telescope hasn't really changed. But with the laser guide star and all the new technology they put in to back correct the atmosphere, it's like having the fog sort of, or defocused image come into focus in front of your eyes. It's just fantastic.
That is absolutely extraordinary. And I guess... I mean, this is the whole point, isn't it? That putting telescopes into space was a great idea because the atmosphere is a real pain in the neck. And so let's build Hubble and a bunch of others and send them up into space. But of course, sending stuff into space, particularly big, heavy things, is really expensive and really hard and prone to failure. And, as we've found out, if something goes wrong in Hubble, it's not like you can just quickly send up another one. And it's not like you can easily get to it and just, tighten the screws. That's really difficult to get into space in the first place and to maintain. So you've got, on the one hand, the benefits of no atmosphere, fantastic. The downside is, but that's a real pain in the neck. So you've lost a pain in the neck and you've gained a whole new one. Yeah. This technique allows you to do it on the ground where a human being can literally get in there and tighten up the bolts if needed. But you can adjust for really, really well the effects of the atmosphere. That was why we were putting stuff into space in the first place.
Exactly. And we will still need to put things in space. I mean, let's not forget that we've got the James Webb coming up as well.
Yeah.
So particularly in infrared wave bands, there's a lot of absorption that happens in the atmosphere, depending on exactly what wavelength you want to look at. So James Webb is going to be looking at those areas that we can't see from the ground. Right. So it becomes complementary in some ways.
So you've got all these different frequencies of light, wavelengths of light. The optical can get through the atmosphere pretty well, which is why we call it optical. We can see that bit, and it comes through quite happily. And so building an optical telescope with all this stuff works really well. But there's only so much you can do at other wavelengths. And if your wavelengths get trapped or get absorbed or scattered by the atmosphere, you can't adjust for that. You can't make more light from the object you're looking at. And so that stuff still needs to go into space.
Definitely, yep.
Cool. So what's the ultimate end point then? The Giant Magellan Telescope is going to have, what did you say, something like 10 times the resolution of Hubble?
Yeah.
So what's that going to allow us to do? What does that get for us?
Well, I thought, okay, let's dig in and look at the science cases, because, I mean, the science cases for these instruments are fantastic. They'd
have to be, because you're spending $1 billion on it,
they
right?
Have to be, of course, yeah. But they're so visionary and they're so exciting to read. And so I thought, okay, let's go and get the
All right,
book.
Sell it to me. I've got $1 billion, and I could spend it on that, or I could spend it on something else. Tell me why I should spend it on this.
Well, so GMT produced this book. It is called The Science Book. Mm-hmm. The latest edition is 2018. I thought, oh yeah, I'll flick through the science book and just get some ideas of what their key scientific key goals are. The science book, it's 208 pages long.
Okay, there's a lot of science in that.
And I read a bit of it. I won't lie, I didn't read the whole thing.
Is it a page turner, Emily?
Well, no, it actually is it's very well written. It's very exciting. It's got some lovely pictures in it as well. But I thought, I started reading the first bit, which is
Can you download this?
You can, yes.
Oh, we'll put a link.
Yeah.
Fantastic.
I've read some bits about the exoplanet science that we're going to be doing. So looking at detections of exoplanets using the radial velocity method. So this is looking at the color change of stars, and by the fact that the stars are changing color means that they're changing position in the sky, wobbling to and fro away from us and towards us. And that's an indicator of an exoplanet being there.
Right. So this is not looking for the brightening and dimming of a star as a planet goes in front of it and then around behind it. This is the fact that when a planet goes around the star's actually in orbit as well, that the planet and the star are in orbit around their common center. And typically, the star's much bigger than the planet, so it's just doing a little bit of a wobble around a center of mass point, probably somewhere inside the star.
Yeah,
but it is doing a little wobble, which means sometimes it's just slightly wobbling towards you and sometimes slightly wobbling away, and you can detect that.
You can detect that, with the color change of the star. So at the moment, we are getting reasonable detections with some of the best spectrographs in the world. HARPS is one of them, for example. We're getting down to meter per second. So this is the velocity of the star that we're measuring here.
That sounds impressive.
Yeah, we can measure the surface of the star moving at about a meter per second.
That's pretty good.
The instrument they're building for the GMT is expected to be at least as good as 10 centimeters per second, maybe 1 centimeter per second.
Wow. Okay. So that will be able to detect these tiny wobbles from presumably much smaller or more distant planets. Is that the idea?
Smaller things. So things like the Earth have a very, very small effect on the star. So if you want to find an Earth-like planet, then you've got to look for very, very tiny wobbles.
Yeah, I mean, the sun's much bigger than the Earth. And so the Earth's wobble, its orbit, is much, much more impressive than the sun's wobble from the effect of the Earth. But it is there. And that's the sort of thing that we could detect with this?
Yeah, that's what they're looking for in the closest sort of stars.
Wow. So Earth-sized planets causing a sort of down to 10 meters or 1 meter per second wobble. Centimeters. Sorry, centimeters. Off by a factor of 100 in the wobble of the star. Wow, okay.
That's amazing.
All right, I'm hooked already.
Yeah. We're going to get images of the closest planets. So for example, Proxima b, this is the closest star that we have to our sun. We know that there's a planet there that was discovered a couple of years ago, Proxima b. We're hoping that we're going to be able to take a picture of that.
Of the actual planet?
Yeah.
Of the thing itself?
Of the thing itself.
We've never done that, have we?
We have sort of in some cases. We've been able to see some of the larger planets that are quite far away from their host stars, some of the things that have disks and therefore have clumps in the disk that we think are planets.
Right.
So, yeah, we have had some images, but we're hoping to get a lot more from the nearest stars in the optical directly.
Okay. So, and being able to see that, I mean, on the one hand, it's just, wow, that's another planet. But presumably there's more to it than that you would actually be able to infer or directly detect. So what's that made of?
Exactly, yeah. So we're looking for biosignatures as the other key part of exoplanet
You could
science.
detect the atmosphere, you could detect what's actually coming off this thing and see what's on the surface, what it's made of, what's there.
Yeah. So that was fascinating read. And that's just the exoplanet section.
Okay, so that's okay. You've already got my billion, but
okay. I'm not going to tell you all of science because there's far too much in 208 pages.
Folks at home, go and read it for yourself. It's a cracking read, I'm sure.
But let me just tell you the headings.
Give us the headings.
They're quite exciting.
Yep.
Okay, so we're also going to learn about the birth of stars, the death of stars, galaxies, their growth, their evolution, the Milky Way, our closest neighbours, gas and how gas works in galaxies, cosmology, the dark universe, the first light of the universe, and the reionization epoch, which I think we've mentioned on an earlier episode as well.
So basically everything from planets to the entire universe from beginning to end.
Yeah, that's a good summary.
Yeah, and so in that regard, being able to squeeze all of that into 200 plus pages is actually not a bad effort.
No,
I would have thought
they've done well.
Yeah, they obviously had a very good editor. Wow. Okay, so which one of those are you most excited about?
Ooh, that's a good question.
If you had to pick one and go, that one.
I think I'm very excited about spectrograph. I do spectroscopy as my bread and butter science.
So which bit is that? Sorry.
So this is the 10 centimeters per second,
Right.
1 centimeter per second. The precision that you can do. I mean, because this is a technique that I use as well in my study for stars. So being
because you look at stellar wobbles and all sorts of stuff. And so that's the star doing stuff. Independent of the planets, that's just the star doing things, which presumably then this could do as well.
Yes.
If it can measure, centimeters per second worth of wobble, due to a planet, it can measure that kind of wobble due to anything.
Indeed, yeah. So we're
Starquakes,
looking
the
for
works.
very, very small pulsations and other sorts of effects, like even some of the solar-like stuff that we can see would be really, really exciting to measure.
So what's beyond that then? There's a huge amount of science that we're going to be doing with that, but I'm guessing that people aren't sort of sitting on their hands and going, well, that's it. That's astronomy done. That's telescopes done.
Oh, of course.
There's always bigger.
There's always more.
So what's my next billion going to be spent on?
So if you look back over the history of building telescopes, it looks like we can double the size of a telescope about every 30 years.
So that's astronomy's Moore's law.
Yes,
Yeah.
yeah, exactly.
Okay.
Which is very exciting.
Mm-hmm.
So, the 30 years is to another double size. In fact, we've already started planning for some bigger telescopes than even the GMT.
So you're saying in a couple of decades we'll have an optical telescope which is basically, 100 meters in diameter?
Well, funnily enough, they did start out with an idea for a telescope which was 100 meters in
Really?
size.
I was joking, but you're not.
Well,
you're not kidding.
yeah, okay. And then it sort of turned into a couple of projects, one of which was cancelled, called the Overwhelmingly Large Telescope.
Yeah, I mean,
That one just didn't
that's a shame
get funding.
because that's such a good name.
OWL,
Yeah.
it's really nice. But we do have two other awful acronyms for telescopes.
Yeah.
We have the EELT.
Mm-hmm.
It was just the ELT, but now it's the EELT. Do you want to have a go at what that one might
The
be?
extraordinarily emphatically large telescope.
You're pretty close.
Yeah.
It was originally the extremely large telescope.
Yeah, the
And-
ELT.
And the Europeans got on board, and it's the European extremely large telescope.
Okay, so we've got giant, now we've got extremely large. We've abandoned overwhelmingly large. Are we getting close to terrifyingly large?
Well, you could use that in the next one. So the next one's the 30-meter telescope.
Yeah. So
TMT.
sorry, the EEMT is how big?
So that one's 40 meters.
And what's the deal with that?
So we're going to build that in the Atacama Desert. So it's it's in Chile as well, but different location.
Okay.
And 2025, maybe they're looking for first light for that one.
Okay, so that one actually might beat the Giant Magellan.
Yes. So both of these two big ones actually are using the other way to build big mirrors, which is like 1 meter hexagons.
Right. What's the deal with Chilean telescopes? Is it just that it's desert, so it's really clear and dry, so you don't have to worry too much about the atmosphere, and it's high up?
High up, yeah,
Right.
high and dry. Those
Yeah.
are the two things we really love about Chile.
Yeah.
And then the other one is TMT 30-meter telescope, which I'm
30
surprised that
meter.
things can
I was
do
about
it.
to ask you what TMT stood for,
Yeah.
but you just told me. Yeah.
Yep.
That's boring. Hang on. Someone needs to talk
It
to their
could be
marketing
called the
team.
terrifyingly mutinous.
Terrifyingly
large.
majestic. Yeah.
Yeah, something like
Yeah.
that.
Someone should talk to them.
2027, looking for that one.
Right.
So
So a
little
whole
bit-
bunch coming online in less than a decade.
Yeah.
We hope. All
And that
going
one's
well.
northern hemisphere as well, which is really interesting. So we can, look at different parts of the sky, of course.
Of course, because Chile's southern hemisphere. Yeah.
So Mauna Kea is the proposed site for that one.
Which is
Hawaii.
Yeah. Okay. So, and that's 30 meters.
Yes.
So we're getting a bunch which are all roughly-ish to within a few meters of the same size. Because the GMT is, what did you say, 24?
24.5.
Yeah. And the EEMT is
EELT, yep, 40 meters.
The EELT is 40, and then the boringly named 30-meter telescope is 30 meters. So, but okay, so they're going to be complementary in the sense that they're in different hemispheres, and they're all very big. So, in about 10 years' time, like you've got 10 years to really get a ramp up onto some amazing new astronomy here. It's going to be a fun time.
Yeah, well, they're already predicting that the demand is going to outweigh supply by these telescopes by factors of maybe 100.
You'll have astronomers lining up around the block.
Yeah, because if you think each of these telescopes is only going to have maybe something like 320 nights per year available. The remainder, you get a little bit of bad weather, not too much in these places, but a little bit.
That's the point. That's
you also
why
have
Chile.
Quite a lot of downtime for mechanical stuff, servicing, etc.
Well, particularly as, these are pushing the boundaries so much, there's going to be stuff. There's going to be things, we didn't think of that, or that didn't work as well as we thought, or we've got to adjust, or whatever it is.
So these are going to be some of the most competitive telescopes that you can get time on in the world.
Wow. So even
we've ever had.
Even with 3 of them coming online within, a couple of years of each other, there's still going to be a queue around the block of astronomers going, are you done? You done yet?
Well, just think about all the stuff we're going to learn in the next few years before then. I mean, we've got TESS up there now.
Yep.
We've got James Webb that's going to fly very soon.
Really hope. Come on, James Webb.
We've got so much that's going to come that we're going to just be like, I just wish I had a 30-metre telescope to go look at that with.
Funny you should mention, we've got 3 of them coming online round about now. That brings us to the end of this overwhelmingly large podcast edition. Look, Emily, I don't really know where we go from there. We just talked about some of the biggest astronomical observing things on the planet. I'm going to have to take a little bit of time to just process all of that. While I'm doing that, I guess people could write in with their questions and comments, couldn't they? How would they do that?
They would shout us out on Twitter. Mm-hmm. So we're at SyzygyPod, and you can write your few characters to us, or you can write us longer messages through our website.
That is right, syzygy.fm. And we're on the other social medias as well. We're out there on Facebook. You can find us as SyzygyPod on Facebook. In fact, pretty much anywhere you find us out there on the interwebs, we are at SyzygyPod. If that's what you search for, you'll probably find us. And what can you do? You can send us your questions. You can send us your comments. Tell us what you think. The other way you can tell us what you think is by leaving us a review. We'd love that. A couple of stars, 5 ideally. If 5 is the maximum, give us that, and it helps us to rise up through the noise. So go to Apple Podcasts or Spotify or wherever you get your podcasts from, and tell the world how much you enjoy this little podcast. But otherwise, I'm just going to go and process all of this information that I've got about overwhelmingly large mirrors doing crazy things. And Emily's just going to hoot to herself for a while. And we will be back again with some more astronomical goodness in about a week. So we'll catch you then.
See you later.
Bye-bye. Looking out of the window of Emily's office, and there is an enormous... It's the giant Magellan lawnmower going past our window. So we're just going to wait for a minute. To be fair, he does look like he's having a good time.
Yeah, but the grass didn't look that long.